Hi everyone, I'm Arash Burdanpani from TU Berlin. Today I'm going to present our work, the Augmentation-Speed Tradeoff for Consistent Network Update. This is a joint work with Monika Hensinger, Ami Paz, and Stefan Schmidt. Nowadays, networking requirements are changing much more dynamically and much more frequently. To adapt to these dynamic changes, we want to use SDNs, software-defined networking. The SDN would allow us to do all these changes in a central manner, much faster, much cheaper. However, it could come with its own challenge. For now, let us look at this subnetwork as shown here, and we will use the rest of the network in the remainder of the slides. The challenge that we want to tackle today is non-consistent update times. The updates might be realized in different time in switches, and this might be due to the fact that we have delays that are inherent in the network, or there might be fundamental defects in the switches, and as you can see in the picture on the right, this would result into a varying time when we have updates in different switches. Now let us see what happens when we have these different delays and different update times. What problems does it cause? Let us see the first problem with this non-consistent update times via an example. Consider the blue initial configuration on top and the orange final configuration on the bottom. And let us assume that the updates for the fourth and the first are done quicker relatively to the other switches in the network. What would this result into is that we would have a loop. The packet would be stuck in this loop until the next update, and it might be dropped, or it wouldn't reach the destination as we wished. This is the first problem, but there is another challenge that we want to also look into. For this challenge, we will consider the rest of the network that we had. In this example, to describe in the next challenge, let us assume that we have a blue packet and a green packet. These blue packets, it would initially go from the top route and then from the middle route, and the green packets initially go from the middle route, then they would go to the bottom route. Now let us consider the case that the blue packets are updated much sooner than the green ones. What happens is that both green and blue packets would use the middle path. This would result into congestion because the middle path has capacity 4, and now we are moving 8 packets along it. So now let us combine these two problems and see what our goal would be for this paper. The goal here is to solve a problem in which, as an input, we are given a network. In this network, multiple source and destination pairs are determined. Each link on this network can have different capacity, and the update time on switches are not known prior to the when we want to deploy our updates schedule. With these assumptions, we want to gather the updates into a set of rounds such that in each round we don't have any congestion or loop, and gathering all these rounds together, we want to have the minimum number of rounds in total. Our solution for the stated problem is augmentation. This augmentation can be additive augmentation or multiplicative augmentation, which is shown by the parameters alpha and beta. The augmentation can be seen counterintuitive. How we can realize this augmentation? First of all, we don't need these augmentations all the time. These are only temporal augmentations. Secondly, these augmentations can be described and implemented via buffers. These buffers can handle small bursts, which are the augmentation that we need for our system. We are the first to consider this augmentation in our work. The previous work mostly focuses on how we can provide loop-free update schedules. There are some works that have considered that the case that we have no congestion and we cannot tolerate any congestion, but the works there are limited. The works on the loop freedom, they show that we can update in n rounds, and sometimes we n rounds. Also, we know that if the 2-round update exists, we can always find them. But if there is no update in 2 rounds, we cannot find them, and it's an NP hard problem. Other works in this area have focused on the solving variations that we have waypoints or synthesizing the solution for this problem. So more formally, in our solution, we will consider augmentation, which is a new dimension. With this new dimension, we will provide algorithms that would reduce the number of rounds that we need, essentially increasing the speed. And also, we will show that we can solve some instances that cannot be solved before. To support our algorithms, we have proofs that shows that any update schedule with twice augmentation can be realized, but with any less augmentation it's not possible. Let's look at this impossibility result first. To show that finding the optimal solution in polynomial time is not possible, we do a reduction from 3 sets. The details of this reduction is in the paper, but as an overview, what we do is we transform an instance of the 3 set into a set of paths. For each clause we have a set of paths. For each variable we have a set of paths, and we combine and match all the paths together using blocking gadgets. Given this hardness proof, should we lose hope? Definitely not. What we have done is we have provided a mixed integer program, as you can see here. This mixed integer program, on top of having multiple objectives that we can adjust based on our needs, it do a set of initializations, and then it would go into 3 blocks, 1 block for loop to ensuring that we have a loop-free update schedule, 1 block to ensure that all the passes that we have, the flow on those passes always go from source to destination, hence all the packets will go from the source to destination, and then we ensure that none of these flows would violate the capacity rules that we have on each link. To ensure the loop freedom, what we do is we use Miller-Tucker-Zimmelmann formulation. This is a known formulation in other settings, what we used in our setting to enforce an ordering among switches, and with these orderings we can ensure that we never have loops anywhere in our networks when we are doing our updates. To ensure that the flows that we have will remain on the path that they should, we use a branch and merge points when we have our flows, and using these branch and merge points and the constraints that we can see in the picture, we will be sure that all the flows would go on the strict paths that have been defined before. And also the congestion freedom, we can adopt it for the additive or multiplicative augmentation to ensure that none of the flows that we use go above the threshold set by the initial capacities and these additional augmentations. The mixed integer program might run slow in large instances, so what can we do for those instances? We provide a series of algorithms. The first one is the greedy algorithm. Its main focus is on optimizing the number of rounds. And for that, what we do is we start from the terminal node, and step by step, we will update as many switches as we can. And we can prove that this program would terminate by induction, because at each step we will have a link that is being updated from the old path or the old configuration to the new configuration. Now, based on this greedy algorithm, we will go back to example that we had, and for such an example is that the problem is congestion based. If the greedy algorithm doesn't provide good augmentation, we reduce this augmentation by delaying selected flows. We do a iterative search to find those flows that would reduce the augmentation the most. And then by doing step-by-step procedure, we can lower the augmentation as much as possible until we cannot lower it with this approach. We run our algorithms for the instances that came from Internet Topology Zoo, and we generate the initial and final configuration based on realistic settings that we can think of. And for those, for varying number of flows and for varying number of routes, what we saw on average is that with a little additional multiplicative augmentation, almost all of the instances will become feasible, so we can route all the instances, and the number of rounds would reduce significantly, which means that the updates would have a significant speed up. And to compare the results that we have from the mixed integer program and the gradient delay algorithms, what we do is we run those algorithms on different number of rows and different number of flows. As we expected, the mixed integer program would perform well mostly on the cases that we have low number of nodes or low number of flows. But to compare the outcome of the mixed integer program from the fast algorithms that we had, we fixed around 250 flow instances and took average on all the instances of graphs that we have from Internet Topology Zoo. And as you can see on the pictures on top, both greedy and delay algorithms would work pretty well on the number of on the additional augmentation that they need to update to provide fast update schedules. In a nutshell, what we have done is we introduced a notion of augmentation for the consistent updates, where we are concerned about congestion and loop freedom in our networks. This notion of augmentation can be realized by buffers in networks. From theoretical point of view, we showed that any update schedule can be realized by twice augmentation, which is relatively a lot. And what we showed that with 2 minus epsilon augmentation, there are instances that we cannot have a feasible update schedule. So what we can do to find a sweet spot with these two parameters, we first developed a mixed integer program that we can adjust based on our needs. And also, if we don't want to find an optimal solution with a mixed integer program because we have limited time, we have provided fast algorithms that work pretty well in the instances that we got, for example, from the Internet Topology Zoo. Thanks for listening and hope to see you in future presentations.